In the last video, we discussed what is multistaging. This schematic which is shown in this video, it represents again a multistaging case. It is a two-stage compression case with flash intercooler. This is a two-stage compression case with a flash intercooler. This box which is shown over here, this is the flash intercooler. And what is happening over here, you see that there is a compression in the first stage, then there is an intercooling in the flash intercooler, and then there is a compression in the second stage, and then there is condensation and expansion. Okay, so if you want to represent this process of two-stage compression with flash intercooler on a pressure enthalpy diagram, let me try doing this. So what I do is, I will try to represent this on a pressure enthalpy diagram. So this is, let us say, the vertical, this is the horizontal, this represents the pressure, this is the enthalpy, this is the vapor dome. We are compressing the refrigerant from the evaporator pressure to the condenser pressure, and this is done in two stages. So in the first stage, compressor 1, you compress, then there is a intercooling in the flash intercooler, and then there is a compression again in the second compressor, and then there is a condensation. After condensation, what you see is that there is an expansion from the condenser pressure to the evaporator pressure, and there is some flash gas which is generated. This flash gas which goes over here, this flash gas has to be compensated by M2 minus M1. So what you see over here is this. So 1 to 2 compression, this is 1 to 2 compression first stage, then flash intercooling 2 to 3, 3 to 4 is compression in the second stage, then 4 to 5 is condensation, 5 to 6 is 3 to 4 is okay. This is 2 dash in my nomenclature, so just let me correct this. This is 2 dash intercooling, 2 to 3 is second stage compression, this is 4, this is 5, and this is 6. Okay, so in this loop, there is a mass M1 flowing, and in this loop there is a mass M2 flowing. So the power consumed by the compressor 1 would be M1 into H2 minus H1, and power consumed by the compressor 2 would be M2 into H3 minus H2 dash. Okay, this should be clear from here also. Power consumed by this would be H2 minus H1 into M1, and compressor 2 would be H2 dash minus H1, H3 minus H2 dash into M2. Okay, and the refrigerating effect would be across the evaporator. So the refrigerating effect would be M into H1 minus H6, and that M is M1. That M is M1. Okay, this is refrigerating effect, and the COP would be refrigerating effect upon power consumed by 1 plus power consumed by compressor 2. So what is important in this case is we need to understand, okay, how this expression has come, this expression has come, this expression come, and we need to determine this M1, M2, and hence the COP from the energy balance. What is the energy balance for this flash intercooler? This is the energy in, this is the energy in, and this is the energy out. Okay, so it would be M into 1 into enthalpy at 2 plus M2 minus M1 into enthalpy at 5, and is equal to M2 into enthalpy at 2 dash. This is the energy balance for the flash intercooler. I hope this is followed. Okay, this is one typical case where we are using a flash intercooler with two-stage compression. We have not removed the flash gas. Okay, and this is an interesting possibility of designing a multi-pressure refrigeration system. In the next lecture, I will discuss the use of flash intercooler with flash gas removal.